Hello? Can you hear me?
Yes, Jan.
Yes, Jan.
Hello?
Yes.
Okay.
Yeah, I can hear.
I will, okay. In the previous lecture, I give you about some homework or assignment. Now, in this class, I will provide you solution before we go to the next one. Okay. Okay. From the circuits that show in, can you see my slide?
Yes, John.
Yes, Jan.
Okay. From the circuit that show in the following figure, determine the inductive component of the unknown impedance ZL that is absorbed the maximum power. In this case, the circuit structure is already very simple in the transmission section. Okay, the key is you must convert, okay, the sinusoidal voltage source into the phasor form, and you must convert the resistance and the capacitance into the impedance form. Okay, the first step, the phasor representation of the circuit can be sketched in the figure D in here. Okay, 3. You can see that is the magnitude of this voltage is 3 at the minus 3 degree. 3 is okay at 3 degree, and here. Sorry, wait a minute. One. Yes. Okay. The key is that, okay, the key in this step also, this will be minus 3 degree, okay, and this, okay, the impedance we will convert into, can compute from the resistance and the capacitance by the omega in this case. The omega equal to 100, okay, okay, for the resistance, ZR is already equal to R, 500 ohm, okay, but set C equal to 1 divided by J omega C. 1 divided by J omega C is, omega is a 100, okay, C is a 10 microfarad. Substitute them, it gives you that C equal to minus J 1000. Or you can write them into a single complex impedance is 500 minus J 1000 here. You know that from the maximum power transfer theorem, ZL will receive the maximum power in the case that ZL equal to ZTH conjugate. ZTH conjugate. And the ZTH equal to 500 minus J 1000. Therefore, ZL equal to 500 plus J 1000 ohm. Yeah. That's the inductive load in this case. The inductive load in this case, the general form of the inductive is J omega L, okay? You compare between the left hand and the right hand. You know that the omega equal to 100, okay? Therefore, you can determine the inductance. The inductance is equal to 10 Henry for this case, okay? Now, we go to the third section. The effective value of the current and the voltage. The effective value of the current and the voltage is present in here. The effective voltage is a measure of the effectiveness of the voltage source is delivering the power to the resistive load. The average value of the size wave power is 0, but the effective value of the size wave is not 0 yet. The application of the effective value is the most power outlet delivers a sinusoidal voltage is typically encountered in the North American frequency of the 60 Hz and the voltage is 115 volt. Elsewhere, a frequency is 50 Hz instead and the voltage is 240 volt. Okay. Now, for a periodic waveform, the effective value of any periodic current is the value of the direct current which deliver to the same average power to the resistor and do the periodic current. The general mathematical expression for the effective value of the current is easily to obtain. and the average power delivered to the resistor by a periodic current can be computed by this formula. Okay, you can see that the first one is, okay, you integrate the signal in one period. We call them the average of them, or the mean, right? The mean, the average or the mean of them. Okay, this here, square, right? Square root, okay? This is the average power in this case, okay? Where the period of this is T, you integrate in one period. The power delivered by the direct current can be written in this form, P equal to I effective square R. Or you can write them evaluate equaling the power expression and solve for the I effectives. We got the effective square root or the root mean square by this definition. Remember this definition, okay? This equation. This equation is not only used for the current, but it can use for the voltage computation. The effective value can compute by root, mean, and the square. You can see that when you compute them, okay, you can see that square root, the first one, you meet the square root first, right? The square root, okay? You integrate them and average them in one period. It means you find the mean of them, okay? The integrate and divide by T is operator of the mean computation. Okay, the last one is I square, right? I square. Therefore, the formula in this case, we can use the definition to be root mean square, or the RMS, okay? Now, the next one, the general, okay, the general form of the effective value of the root mean square is we frequently apply them on the sinusoidal waveform. The most important special case is that of the sinusoidal waveform. Let us select the sinusoidal current will be in the general form in here, IT equal to Im cos omega t plus phi, where the period of I is equal to 2 pi divided by omega. And substituting the equations 19 to obtain the effective value into this. Okay, this is the I effective in the root mean square definition, square root, mean, and the square in here. Okay, I effective value equal to I cos, okay, square here, cos square. Cos square, you can use the trigon to formulate them to be the constant plus with this cos 2 theta, okay? And you integrate them in one period, okay? The period of them is equal to 2 pi divided by omega, 2 pi divided by omega, okay? You substitute one period of them. Now, when you integrate them, what happened? You integrate the constant, give you, okay, yeah, but you integrate the cos, okay, integrate the cos in one period, give you 0, okay? You substitute them, give you here. Okay, therefore, it's have only this term ref. Therefore, the general form of the I effective, you can summarize that for the sinusoidal waveform special case, okay? I effective value equal to I peak or the I maximum divided by square root 2 or 1.4. Thus, the effective value of the sinusoidal current is a real quantity which is independent of the phase angle and equal to 0.7 times the amplitude of the current. Okay, in the graphical file of view, the relationship between, okay, the sine wave and the effective value of the root mean square can compute by this step. The first one, you determine square, right? Square is mean you make, if it's negative, make them positive first, and the magnitudes of them you take square. Okay, take square. Okay, you integrate them and average them in one period. Okay, integrate them, it means you determine the area under this curve and find that. Okay, area under this curve in the averagings. Okay, give you here. After that, you take the square root in the final step. Take the square root in the final step. This is the step of the computation. The root means square, or you can compute them in the sinusoidal waveform equal to Im divided by square root 2 or equal to 0.7 Im. Next one, the average power. The use of the effective value simplifies slightly the expression for the average power delivered by a sinusoidal current or the voltage by avoiding use of the factor 0.5 in here. Therefore, since the I effective, okay, equal to the I max, okay, 0.7 Im, okay, the average powers may be rewrite into this form, right, in the term of the I effective, or express them in the term of the IM in here. The other power expression may be written in the term of the effective value in here. Power equal to IV cos theta. Okay, cos, okay, the theta minus phi, the cos, okay, the angle difference between the voltage and the current. Okay, or you can write them, okay, the power equal to V effective value square divided by R. The power transmission or the distribution and the rotating machinery, such as the motor, okay, or the generator. The effective value is usually used in that model. In the case that if your circuit have more than one generator that have the different frequency, for example, the first sort may be operated at the 50 Hz, the second sort may be operated there at the 60 Hz instead, okay? How to compute them, okay? We must compute the I effectives, okay? The effective value of each may be the current or the voltage at each frequency first, okay? In order to determine the effective value of the periodic or non-periodic waveform, which is composed of the sum of the number of the sinusoidal of the different frequencies, we may be used the appropriate the average power relationships written in the term of the effective value of the several components by this form, or you can write them in the term of the current is here I effective of equal to the square root I effective of the frequencies, the first frequency, plus with I effectives, okay, of the second frequency square, plus with the I effectives of the third frequency square, and so on. From this, we see that the effective value of the current, which is composed of any number of the sinusoidal current of the different frequency, can express in the equations 24. Okay. Therefore, you can compute the effective value in this manner. Okay. Okay. Now, in order to give you more understand, okay, I will give you 15 minutes to compute this effective value of this value. Okay. We have, can you see my slide?
Yes.
Okay. We have 4 questions. Okay, you can compute by hand. Maybe each question maybe 2 minutes or 3 minutes at most. I will provide you 15 minutes and finish that. Okay. Try to compute them, and I will provide you complete computation step in after 15 minutes. But if you finish first, you can post them in the meeting chat, and I will checking to you. Okay, it's right or wrong. Okay. Stop sharing in 5, 4, 3, 2, 1. Okay, I will check your attendance. Okay, can you hear me?
Yes.
Okay, we're checking your attendance. Identify yourself by open the camera now. อ้าวสิทธิพงษ์ยังไม่ตื่นอีกเหรอบิดขี้เกียจใหญ่ วินเซนต์ Hi Jimma are you okay
I'm okay, sir.
ปูคาน your camera is not working not fix it yet if in the final you cannot solve it okay your paper cannot be grading okay and you may be retake exam in the maybe in classify as you are missing okay ชนนิการเป็นไงบ้าง Okay, I will give you another 10 minutes, okay, quickly, let's do it, okay, and I will provide your solution and we continue to the next part, okay. In this lecture, we will finish, okay, this chapter.
Achan, how many chapter we need to study for final exam?
In the final exam, you can
Yep.
see in the course outline.
Oh, thank you, Achan.
Never see it again? You should not ask that if you used to see it or you to read it, okay? But the
Yes.
next time in the Monday, okay, don't forget to remind me. I will provide you the final exam information. Okay, how many chapter exactly, how many quota for each of them. Okay,
Thank you, Achan.
you're welcome. Or do you want to be surprised?
No, Achan.
Okay, let's do it now first. Oh. Hello, can you see me? Can you hear me?
Yes, Ajahn.
Yes, Ajahn.
Okay, okay, I think some of you maybe finished some part of them, but maybe not all, okay? I will provide you the first two solutions, okay? And I will provide you time in another 10 minutes to finish D and C and D, okay? Now, the first one, okay? A. The A is very easy, okay? Because the function is, okay? This may be the voltage or the current, we don't care. But the effective value is, okay? You write them, convert them into the phasor form first, okay? 60 degree, okay? 60 degree. And by this, the peak of them, we use the maximum magnitude, the peak of them, the amplitude of the phasor, okay? And divide by square root 2, okay? Divide by square root 2 or multiply by 0.7, approximately that. In this case, it gives you 4.24 volt. The next one is a little bit more complicated, okay, because it's comprised by two functions. Two functions, we use the same technique, okay? We convert them, okay? Use the phasor to combine them first, or the trigon to combine them, okay? It will be cos A, okay? It will be expressed by here, okay? And you convert them to be here, okay? And merging them, okay? Merging them and this thing, okay? This, okay? We convert this, okay? 6, okay? This is 60 degree, okay? 60 degree, okay? This is before, okay? Cos, okay? 120, sorry. This may be a little bit wrong. Okay. Yes. Cos, okay, convert them to be here and here. Yes. Okay. By, okay, can you see the slide? Okay. By this, okay, the second one, you use the phasor, converts the first form and the second, okay, the first function and the second function into the phasor form. The first is already equal to 60 degree. Okay. The second one will be sine wave. You must convert them to be the cos function and by, okay, minus this 60 degree, okay, 60 degree instead, okay? Here, convert them into the phasor form, okay? And multiply by the magnitudes of them. Comprise, in this case, you must adding them. Therefore, you must convert them into the complex function, okay? The complex function instead. After you adding them, give you 6 minus 3j, okay? 6 plus, oh,
อา
sorry,
จารย์ครับ
6 plus, anything?
90มาจากไหนอาจารย์
ฮะ อันนี้ต้องเป็น60นะโทษทีอันนี้ต้องเป็น60น่าจะต้องเป็น60แป๊บหนึ่งเดี๋ยวแก้ให้
It's supposed to be 60, right? Not 120.
yeah 60 minus 60 okay yep okay
อาจารย์ครับ
okay here is have
ทั้งหมด
minus 90 degree because you must convert sine to be cos function right we shift by 90 degree เปลี่ยนจากฟังก์ชัน sine เป็น cos ต้อง shift ไป90 องศาถูกไหมนะ shift ไป90 องศาafter we get here okay we convert them to be the phasor right 4 at the minus 60 degree 4 at minus 60 degree right and you convert them into the complex number from the phasor you convert them to be complex number we will give you here why we convert them to be the complex number because we must adding between the first term and the second term you know that the phasor is suitable for multiply and division but the complex number will be suitable for addition okay real part you add with the real part imaginary part you add with the imaginary parts okay after that okay after you get here you must convert them into the phasor first okay because we must bring okay we must use the magnitudes of them 8.7 okay divide by square root 2 okay 8.7 square divided by square root 2 give you VRMS clear do you have any question okay I try to produce you okay in the detail okay provide you review you in the detail but remember that in the final if you don't do by yourself you cannot do it in time if there were If you are so lazy, it's the first time you just do it, even though you know how to do them. But if you're not fluent in, okay, you never do them before, okay, or you the same way that you know how to integrate them, but if you never practice, okay, to integrate fluently, you cannot do it in time. Okay, be careful about that. Okay, the C and the D, I will give you another 10 minutes and we'll provide your solution. Okay, the same technique, but here this one you can see that you must for this you must use the tricone, convert them to be the power 1. Remember that the tricone, if the power of the tricone is 2 or 3 or 4, bring them to be the power 1 by use the tricone property. Okay. Okay. 3, C and D, try to finish them, okay, in 10 minutes and I will provide you solution. Okay. Hello, can you hear me?
Yes, Ajahn.
Okay. We have not much time. Okay. The next solution is here, right? I told you before. Okay. The question C, the key of them is you must know how to use the tricone to convert this into the tricone that power 1. If the power is 2, you cannot convert them into the phasor form. The power 1, yes, even though you can convert them, but you can see that 3 values have the different in frequencies. Okay. The first one is have no frequency, is constant. It means omega equal to 0. Second one, omega equal to 25. The third term is omega equal to 50. Therefore, the magnitudes of them, okay, VRMS of each term. The VRMS of the first term is, okay, the DC. You don't not necessarily to divide them by square root 2. Okay, no. Okay, it's already used that. Okay, for the other sinusoidal function, you must divide them by square root 2 or the power 2 is mean you divide by 2 in here. Okay. The second term it have a frequency omega equal to 25. The third term is have omega equal to 50. Okay. The way to sum them, okay, you use the VRMS. The way to sum them is already sum in this form. Okay. The square roots of the first frequency, the second frequency, the third frequency, and all of them we take the square root in the final step. The next one, the last one is, okay, is this term. This term is already provide you 3 components that have the different frequencies again, okay? The first one, you can see that we don't care what about the frequency of them. If the frequency of them is different, the first 4 is a 0, omega equal to 0. The first term is omega equal to 25. The second term, omega equal to 30, okay? You use the same formula, okay? The square root of the VRMS of the first frequency, the second frequency, and the third frequencies, okay? Divide them and take this, okay? Divide by square root, okay? Take square root 2 and divide by 2, okay? And take the sum of all and take the square root in the final step. Now, you know about the IMS, you know the idea of them, okay? Roughly, we will use them. Next one, the next topic is the apparent power and the power factor. Historically, the introduction of the concept of the apparent power and the power factor can be traced to the electric power industry, where the large amount of the electrical energies must be transferred from one point to another. The efficiency with which this transfer is affected to related directly to the cost of the electric energy, which is paid by the consumer. The consumer who provide the load which result in the relatively poor transmission efficiencies must pay a greater price for each kilowatt hour of the electrical energies. The idea of them is, okay, the transmitter, okay, in the power station, okay, the power station provide the power to the load. The key is the load is if your load is already the resistor only, it's easy, okay. The power that you absorb, okay, from the source, you can use them 100%, okay. But in the real world, in general, the power in your factory is usually used to drive the motor. Okay, and the motor's large part of them is the inductor form. Okay, it is the inductor form. Therefore, it's not only the resistor. It has some inductor or it has some impedance that's not real. The impedance is that is the imaginary or the reactive load that came from the capacitor and the inductor, even though it's not consume the power directly, but it will be destroy the performance. Okay, the idea of them we present in this section. Okay, the power that the consumers receive is usually in the complex form, but the really they can use is only the real number. Okay, the imaginary number is the number that they absorb from the power plant, and the consumer must pay for that price. Okay, now about this idea, we assume that the sinusoidal voltage is Vt equal to Vm cos omega t plus theta. Vt is applied to the network, and the resultance, the sinusoidal current, is represented in here. If the voltage is here, the current that is applied in here. Okay, and the apparent power is the The apparent power is mean you multiply between the voltage and the current directly. We don't care what about the phase difference between them. Therefore, the unit of the apparent power is VA. It came from, it's not watt, it's a VA. It came from volt and amp. Okay, it's called the apparent power equal to the effective value of the voltage multiplied with the effective value of the current. Okay. Now, the ratio of the real and the average power and the apparent power is so-called the power factors, okay? The idea of them will be easily to plot them in the graphical point of view, okay? Now, the idea is very simple, okay? The current is a complex number. The power, the voltage is a complex number. Therefore, when you multiply that, okay? Yes, the power to that load or the power from the source is apparent power, okay? The apparent power. But the average power is mean the real power that you can use, okay? You can use, okay? Therefore, you can see that in this case, the power from the source is the apparent power, but the real power that you can use is the average power, okay? Therefore, in this case, the source or the transmitter will charge for the apparent power here, okay? Because your consumer fault that cannot make the power factor to be 1, okay? You can see that in this case, even though the magnitudes of them is maybe double, okay? It means if your power factor system is poor, you draw the power about the 20 or 200 VA. But you use only 100 watt. Another 100 VA is gone due to your pouring power factor, okay? From the pure resistive load. The voltage and the currents are in phase, and theta and phi is the 0. And the power factor is the unity. The apparent power is equal to the average power, perfectly. For the pure reactive loads, okay, the phase difference, theta and phi is different between the voltage and the current is about a 90 degree, and the power factor is 0. It means if your load, okay, is have no resistor, it have only the capacitor or the inductor, okay, the apparent power will be in the vertical axis. If it in the vertical axis, it means no power you can consume from the real use, okay? No, okay? It's only, but you must pay a lot for the apparent power that almost in the vertical direction. The idea of them will be present in this example, okay? From the circuit shown in the following figure, determine the average power delivered to each load, okay? And 2 load. You have 2 load, right? Okay. Determine the apparent power supplied by the source. It means the apparent power is the complex power that generates from the source. Okay, and compute the power factor. You can see that in this case, the first load is not perfect load, right? 2 is a real. The more imaginary load is make you the poor power factor. Okay. Yeah. The second one is okay, the same. Okay. It's the real part is here. The imaginary part is the reactive load. Okay, it's not good. Now, determine the current first, okay? From the circuit analysis, okay, you can simplify that, okay, 2 impedance, you can simplify them to be a single impedance, and you can determine the current by use the Ohm's law. V equal to IR, I equal to V divided by R. Okay, V divided by R or divided by Z. Okay, 0 degree divided by 3 plus 4J. Okay, or it equal to 12 at the minus 53 degree. Okay, or it equal to 7.2 minus J 9.6 amp RMS. Okay, this is the current. Okay, the next step after you determine the current, you can determine the average power absorbed by each load. The average power is came from the real part of this. Okay, real part of each load. The top them, okay, the top of this load, the real part of them equal to 2. Therefore, the power, the average power of the upper impedance equal to, okay, I square R or 12 square multiplied by 2 equal to 288 watt. Okay, 288 watt. Now for the, okay, the right hand side road. Okay, the right hand side road is, okay, P lower is equal to I square R again. I is the same, is 12 square. Multiply with the real part of that. The real part equal to 1. Therefore, the power for the right hand side road equal to 144. Now, it's already see. When you see here, you don't see any interesting issue yet. Okay. until you determine all power that you deliver from the source. The power that deliver from the source in this case, okay? You know that the source equal to the 60, right? The current equal to the 12. Therefore, the total power generated from the source is up to 722 VA. 722 VA. Now, when we plot them, okay, it's about here. The idea, the ratio between, okay, the power that you generate and the power that you are really use is here. The power that absorbed by the top load equal to 288. The power by another load is 144. But the total power that you generate is up to 720 VA. 720 VA is this vector, okay? But this is, okay, it's only the average power that you are really use is only 423 watt. You see that? You generate up to 700, but you use only 400. 400. The performance is only maybe 60%. The performance that you are really use is only 60%. Okay, it's not good. Okay, since the combines, yeah. Okay, from this idea, you can see that the apparent power is the all power that you absorb from the source, and okay, the ECAT must be provide this power to you. But if you use only here by your poor power factor, you use only 423 watt. Okay, it's not fair that you will pay for this. You must pay for all. Okay, pay for all. You must pay for the apparent power. Therefore, when you see in the electrical bill, it will charge you in the watt and in the power factor form. Fortunately, that in your condominium or your house, okay, the power factor have considerably high power factor. Is close to be 1, maybe a little bit, maybe 0.8 or 0.9. And the number of this, okay, the number of the power that you use is not much, maybe 1 or 2 or 3,000 baht, okay. But in the real factory, for example, in the real factory, you may be prepared for the electrical bin, for example, in the AVAC. The Assumption University pay for the electrical maybe several million baht per month. Per month. Okay. Therefore, if the power factor can improve 1%, 10%, okay, you save 100,000 or 200,000 baht. Okay, very much one. Okay. Okay, this is about this idea, and we go to the last part. Okay. Now, after you know about the apparent power you can see them to be the complex power, but it's concentrate only on the magnitudes of them. Okay. Okay. The idea of the complex power. The complex power is here, the thing that you already see in the previous one, but the complex power will be show you the magnitudes and the angle in the horizontal axis. Okay. In the horizontal axis, or it means you must convert them into the real part and the imaginary part. Okay, the complex power, the magnitudes of the complex power will be found to be the apparent power, or the unit of them is VA, 1 amp. The real part of this complex power is called the average power. The unit of the average power is watt. Okay, and now another one definition of them is the imaginary power of this complex power. We call them the reactive power, or VAR, or the 1 amp reactive. 1 amp reactive. The average power is absorbed by the two terminals is given by P equal to IV cos C, cos difference between, okay, the current and the voltage. Okay. The complex power can compute from, okay, from V effective and the I effective conjugate. Yeah. Therefore, the complex power is comprised by the real part and the imaginary part. In the slide, I try to use the color to represent them. Okay. The pink one is represent the complex power. Okay. Explain is comprised of the real. This is a red one is the average power, and the green is the imaginary power or reactive power. Now, in order to give you more understand, I will provide you the example. An industrial consumer is operated at the 50 kilowatt. When you read the instruction, Okay, the unit of each power we will define what about the power is. Okay, for example, here the industrial consumer is operate at the 50 kilowatt. Kilowatt is mean this value is average power or the real power. Inductive load at the power factor 0.8. The source voltage is 230 volt VRMS. In order to obtain the lower electric rate, the consumer wish to rise the power factor to improve the power factor to be 0.95, ranking specifically a suitable solution. Okay, this is okay the old model of your factory, but you would like to add another one that can improve your power factor. Okay, now the first one. Okay, we consider by the old original one first. Okay, in the complex power. Okay, you can write. Okay, draw the sketch of the complex plane power first. Okay, the power in the complex plane. Okay, you know that the average power equal to 50 kilowatt. Okay, 50 kilowatt with the 0.x power factor. 0.x power factors. Okay, arctan 0.x. You can find the angle between them. Okay, the angle of the complex power here. Okay, is cos theta minus phi. Okay, give you power factor, and this value equal to okay. The angle is about the 37 degree. Okay, now okay, you can find the apparent power or the complex power magnitudes. Okay, the complex power is mean the 50 kilowatt divided by 0.8. 50 kilowatt divided by 0.8. The complex power equal to 62.5 kilo VA, kVA. Okay, now by you compute here, you can determine the real part and the imaginary part of them. Okay, you can see that the complex power equal to 62.5 at about the 37 degree kVA. Or you can write them in the real and the imaginary part. The complex power equal to 50 plus 37.5 J. You can see that the 50 is mean the real part of them or the average power. Okay, 37.5 J is the imaginary power or the reactive power. Okay, next one, you said that you would like to corrective device okay, you would like to develop or improve your power factor by adding another one corrective device to your system. Now we brought in the okay the complex plane first. Okay, the power factor. Okay, the power that you still absorb is 50 kilowatt. Okay, the original power. Okay, the power that you would like to set is here. You set the power factor to be 0.59. Okay, therefore the angle will be only 18 degree. 18 degree. Okay, 18 degree. Okay, therefore you write when you write in the complex power is mean it equal to yeah 52.6. Okay, 18 degree, or you write in the complex number in the polar, convert them into the complex, give you 50 plus 16J. 16J is here imaginary power, the new imaginary power or the new reactive power that you absorb. Okay, the difference between the old reactive power and the new reactive power can be plotted in the slide in here. You can see that the original reactive power is consumed 37.5, but the new reactive power is improved to be 16.4 kVA. Therefore, the difference between them, okay, you must reduce the reactive power by minus 21J. Minus 21J kilo. See ya? Now minus 21J kilo. Okay. What about that? Okay. Minus 21J kilo is here. You can find, you know that the power different. Okay. The power different. P equal to IV or I equal to V P divided by V give you the new current equal to here. You get the current. Okay. You can find the impedance. Because the voltage is already fixed, okay? The voltage is already fixed in here. You know the power, you know the voltage, okay? The voltage is fixed, okay? You can find the current to them. And if you find the current, you know V, you know I, you can find R, okay? V equal to IR, R equal to V divided by I, okay? You substitute them. The new impedance that makes the power factor is improved. It equal to minus J 2.5 ohm. Okay. The value, exactly value of them depend on the omega that you operate, okay? If you operate at the 50 hertz, okay, you can determine, okay? You can see that if the impedance is negative, minus J. If the impedance is negative, it means the load must be capacitor, okay? If the impedance is positive, the load must be inductor, okay? Okay. Okay. Can you see my slide?
Yes, Ajahn.
Okay. Okay, capture this question, okay, and try to do and submit them in, okay, in 15 minutes quickly. Okay, stop sharing the slide in 5, 4, 3, 2, 1. Hello, can you hear me?
Yes, Achan.
Okay. Capture the last question is here. This last question. Do you can see? Wait a minute. I will show you a slide. Yeah. Okay. Can you see my slide? Hello? Can you see my slide?
Yes.
Yes.
Okay. Capture the second question. Okay, first. Okay. And both question, I will provide you solution in the next time. Okay, in the next time. Okay, capture it. 5, 4, 3, 2, 1. Okay, finish. Okay. In fact, yes. I would like to present about the exam information in the next week, but I afraid that the next time some student is you cannot prepare in time. Therefore, I will give you idea about the exam. Circuit course. Okay. Okay, in this. Okay, wait a minute. Okay. Can you see my slide in the course outline?
Yes, Achan.
Okay.
Yes.
Okay. It's okay. Chapter 1 to chapter 5 is already finished in the midterm section. Now, the final is comprised by the chapter 6 in the textbook is about the op-amp and it's about the operation about the op-amp and the transistor model that we is belong to the electronic subject, not ours. Okay, therefore we skip to the chapter 7, 8, 9, 10, 11, and 12. 6 chapter. Each chapter, one question, one big question. Okay. Now, in the final, we have 6 questions, depend on each chapter. 8, 1 question. Oh, sorry, 7, 1 question. 8, 1 questions. 9, 1 questions. 10, 1 question. 11, another one. Okay, 12 is 1. Okay. You can see that in the slide. 1, 2, 3, 4, 5, 6. 6 main questions. Clear? Each question 10 marks. Each question 10 marks. And you have about 3 hours for the exam. Okay. It means you have 30 minutes for each question. But okay. Is it enough? For the final exam information, is it enough? Or do you want to know more?
More.
More Achan.
Okay. We concentrate on it. Okay. Can we zoom it? Okay. Yeah. Okay. Now, in the chapter 7, I split into sub-question. Okay. Maybe 1.1 and 1.2. 1.1 is discuss about the capacitor. 1.2 is inductor. For the capacitor and the inductor topics, okay, we have only 4 main quantity that we concern. Okay. The current in the capacitor or in the inductor, the voltage. Okay. If I give you the current, you have the ability to find the voltage. If I give you the voltage, you have the ability to find the current. Clear? And after that, if you know current and the voltage, you already have the ability to determine the power. You know I, you can find V. You know V, you can find I. You know I and you know V, you can find P or the power. Okay. After that, if you integrate the power in the certain respective time, you get the energy. It have 4 main quantity that the questions will ask you. Okay. Maybe ask you, for example, in the capacitor, maybe give you the current, ask you for the voltage, ask you for the power, ask you for the energy, or so on. Okay. Or reverse. Okay. Or in the capacitor, I will give you the voltage, ask you for the current, or so on. Okay. Another 3. I will give you 1 and ask you for another 3 unknown parameter. Okay. Okay, yeah. Therefore, the difficult in this part, you can see that if I give you I, for example, if I give you I ask you for V. If you determine the wrong in this step, V, you get the wrong power, right? P equal to IV. You get V wrong, you get P wrong. If you integrate them, you get wrong. Nothing left. Okay. Now, for the second question, it's about the RL and the RC circuit. The first one is the RL. The second one is the RC. Okay. It's maybe driving short or short free. Checking them. Okay. Checking first. The circuit is a driving short or short free. Is the RL or RC. The way to solve them is different. Okay. The key parameter for RL is IL. The key parameter for RC is the VC. Next one is the RLC circuit. Okay, the third question. The RLC circuit, it have two types of them in the series. RLC in the series and RLC in the parallel. Okay. The series and the parallel may be driving short or the short free. You check from the circuit structure. Okay. RLC in the series and in the parallel, the way to find alpha and omega is different. The formula of them is different. Remember that. A lot of the students remember wrong. Okay. Remember wrong formula. Okay. Therefore, when you determine the alpha, you use okay, alpha and omega. For the parallel, you use the series or you use, okay, the other one. Okay. Next one, for the phasor or the sinusoidal steady state. I give you the circuit and you must convert them into the phasor. Maybe apply the simple KCL or KVL to determine the current or the voltage at the interesting part. Or the question may be give you more. This question will be provide you two sub-questions. Okay, two sub-questions too. Okay, maybe maybe use the RLC in the symbol. Okay, we use the Ohm's law, V equal to IR, or the KCL or the KVL. Okay, or some question may be a little bit more complicated. Okay, you must use the node analysis, met analysis, superposition, short transform, Thevenin or Norton, so on. Okay, in here. Last one is about the complex power. That's I already teach it to you. Okay, we have about the four main topic of this power: the instantaneous power, the average power, the apparent power, and the complex power. Okay, the difference between them and how to determine each of them. Okay, by use the previous skill of the circuit. Okay. If you would like to determine the instantaneous power or the average power in the time domain, you determine the instantaneous powers from the transient circuit analysis and integrate them in the certain of time. Or you may be solve them. If the sort is the sinusoidal waveform, you may be convert the sort and the load to be the phasor and the impedance form, and you can determine the average power by applying on the real part of the road, or so on. Okay, or complex number. The last one is the polyphase or three-phase circuit analysis that we will discuss in the next lecture. Okay, this is all. Okay, this question, okay, the complex power, we will split into two sub-questions. Okay, only the last one, the three-phase, is a big question, big single question. Okay, that we provide you, maybe have a sub-question in them, okay, to ask you about that circuit. Any is all for the 6th question in the final. Okay, any question? Okay, if you have not, okay, see you next time. Okay, for the last chapter, the chapters 12, polyphase or three-phase circuit analysis.
Thank you, Ajahn.
You're welcome.
Thank you.
Thank you.
You're welcome.
Thank you.
Achan, is exam open book or closed book?
Close book, close book, close book. Do you want to get the open book exam?
No, Achan.
I can create the open book, but I don't know you can do it or not. Okay.
No, Ajahn. We would study and expect